we're going to end up where we have a MATLAB program that does the same thing. But first, let's do it by hand. So we went through all these examples and they seem reasonable, the answers. So the method is coming up now. So this is how to do it. From the examples, he creates the rule, right? Now typically if you're a strict mathematician, you derive it, not use an example to create the rule. But for us, we are not interested in the mathematics, so it's okay to use shortcuts. So what she's saying is, for the case, remember the 3, the number, then this seems to work. Try it and you'll get the same answers. That's what she's saying. That means the y shift is placed here, 0 shift for the x and 0 shift for the z, and it's -3. Now all that's going to be formalized. Is it -3 or 3, right? Which frame to which frame? We'll formalize the rule, but right now this works. That also works to convert this point, and that works to convert this point. These are the 4 examples that they gave, and this works for the general case. So we'll formalize the rule shortly. So the point is, our matrix for the general case. So I'm going to cut to the last, there's no point in going through this over and over again. We're going to go to the result. So, there are 2 concepts here. We are looking for the transformation of a vector in the J frame to a vector in the K frame. So we were using the examples of world and robot. So here they just use general, J to K. So always it's the subscript to superscript. We are looking for the transformation that takes a vector in this frame. So you're saying, okay, where did this vector come from? That point, right? The vector is, if you join 0, 0, 0 to that point. So basically by transforming a point, it's the same as saying we're transforming the vector. So imagine a line drawn from those points, what points are those? Any point, 0, 3, 0. So convert from word. So 0, 3, 0 you get 0, 3, and 0, right? So imagine a vector. So if you convert the point, it's like you're converting the entire vector in a sense, right? The vector being the line joining the origin to that point. So that's what she's talking about here. So we need this. This is what we're looking for. The transformation that takes a vector in frame J to K. And the rule is this. The general rule is this. And we're going to confirm it with the MATLAB program. So how do we take a point that is in frame J and convert it to be in frame K? And then there is another concept. How do we compute the transformation between frame J and frame K? These are different. Remember, we originally said we need to pull this frame back?
Yeah.
That's not the same as converting a vector. There's 2 different operations. What does it take to align the 2 frames, and what does it take to convert a vector from one frame to the other? They are 2 different things. T is a transformation, F is what you need to do to align it. Now, you'll be surprised at the answer, but you can go back and look at the examples. It's the other way around. To take a vector and transform it from the J frame to the K frame, you have to figure out how to align the K frame to the J frame. It's the opposite rule. If you go back to the earlier examples, you'll find out that it's the opposite rule. To transform from world to robot, you have to find the alignment between robot to world. It's the opposite rule. We can confirm it, because we're going to try examples. And finally, another example why you need transformations. So this is a mountain. So I guess mountain, because you can imagine a fixed frame there, right? You bury it in the mountain, it's fixed. That's the whole idea. And here is a car that is moving around, and it's 5 units this way, 4 units this way, and 1 unit this way. So you already know the answer. Just by looking at this, you can create your own problems, right? And now we're going to use a MATLAB program to do the transformation. We're going to use the matrix transformation. In the afternoon, we'll do it with quaternions. Now, I think we should do this, and then the second part is angles. Translation and rotations. But first, maybe we should just take care of this. So for that, we need to go to MATLAB again. We don't need gazebo. If I did not load that program, let me know. First, I have to figure out which one it is. I think it's this one. So I'm running some examples of hers, Jennifer Case. Numerical examples illustrating use of the homogeneous transformation operation to transform a vector from one frame to another. So again, the usual, clean up the environment first. Is that okay? So first example involves translations only between axis J and axis K. So from axis J to axis K, a vector in axis J has to be moved to axis K. You already know why we need to do that. Many cameras, many robots, right? So transformations are flying back and forth all the time in robotics. So specify, this is what we want to do, specify the homogeneous transformation to transform a vector in axis J to axis K. So this is pure translation only, and I borrowed the mountain and the car example. So, as I said, we can formulate problems for which we know the answers. So this is the plane picture I imported here. Yeah. Translation only. A equals 5, B is equal to minus 4, C is equal to minus 1. So you're supposed to, for the multiple case, so the multiple case is translations along all three axes, right? Remember, there is no misalignment because the angle we'll do later. Right now, the axes are aligned. Can you see that? Y, Y, X, X, and then Z and Z. So there is no rotation issue. There's only a translation issue. And we are saying if A equals 5, B is equal to minus 4, C is equal to minus 1. Now remember, to transform a vector from this axis to that axis, you have to find the frame alignment from this axis to this axis. It's the opposite rule. Got it? Yeah. To transform from here to here, you need to find F from there to here. T from M to C requires F from C to M. Yeah. Now that was just given to us. We did not prove it because we don't want to be like a math professor here. So let's see if it works. So I have set A equal to 5, B equal to minus 4, C is equal to minus 1. Yeah. Now 5, 6, minus 3, 1. It's in the mountain coordinates. 5, right? 5, 5, 6, minus 3, right? So 5 here will be how much on this? 10, right? So similarly, you can figure out the other two, what the answer is, because there's no rotation. So you can, even if there were rotation, you can figure it out. But because there's no rotation, it's even easier. So we know the answer already, right? It's going to come up here. See? Here, the car coordinates. But this is the matrix according to the transformation rule. This is the homogeneous transformation. Right now there's no rotation. So these 3 by 3, this part here will be a unity matrix. Got it? So if there's rotations, numbers are going to pop in there. But right now it is 1, 1, 1. It's a diagonal matrix. And you put the ABCs here. And the last 4 are filled out 0, 0, 0, 1. So this is the transformation. T form 1, transformation 1, matrix multiplication with reg M, and then you have to do a transpose just to make them compatible. So, and then you run it. I think I did, but I run it again. So let's see if the answer is correct. Is it correct? 10 is correct, 2 is correct, and minus 4 is correct, right? So that's the rule. We played around with y and so on, but then finally I gave you the rule. To transform from here to here, you need to find the frame alignment from here backwards here. You don't get that?
So can you
to align this, yeah. Did you say can you explain it?
Yeah.
Yeah. To align this frame to this, to align the car frame to the mountain frame, I have to go 5 along this direction, right?
Yeah.
And how much in this direction? Z-axis.
1.
1 or minus 1?
Yeah, -1.
So here it is, -1. And the last one, how much? Huh? 5 you said?
-4.
-4. So there it is.
Yeah.
So once you calculate that, just put the numbers in and blindly, do the transformation. The matrix pre-multiplies by m. All these transposes are just to align them. And you get the answer. Here's the answer. 10 to -4. Is that okay? No? Alright, once again. In order to transform from the mountain coordinates to the car coordinates, I need to find out what it takes to align the car coordinate frame to the mountain coordinate frame.
Yeah.
That requires 5 along this axis. If you move it 5 along this axis, this will end up in the same position as that, xy's. Then you also got to go -4 along the y-axis, this way, and -1, this way. So that will align the two axes.
Yeah.
Stack those numbers here. This is the entire unity matrix, 3 by 3. They will accommodate the rotations later. And then the last one is 0, 0, 0, 1. And then do it, and you get the right answer.
So what does this 6 signify
6?
in mountain vector?
You said 6?
Yeah.
6 here?
Yeah.
So 6 is the y direction in the mountain coordinate. So the point is somewhere here. 5, 5, 6, and then -3.
Okay.
So 5, where is the point? Oh, here. 5, 6, -3. The 1 is just, the weighting factor. So 5, 6, -3 is 5, 6, and down by -3.
Okay.
So it's a point somewhere there. I could have drawn the point, but I was lazy. I should have drawn the point here. Is it okay? No, you can put, no, why don't you put something else whose answers you know? Just put something else whose answers you know. Let's do it. So it's easy, right? All you need to do is change this. So give yourself a problem and solve it yourself. And give yourself a pat on the back. Or maybe your neighbor.
So that is the general form of the transform.
For the translation only.
So, like, for the translation.
Yeah.
So we have only the values of A, B, C change, but their positions are the same. Right. This is the formula for that.
Yeah, this is the formula where you have alignment already, no angle shift, and it will handle any point so long as you can read off A, B, C. So then after you do that, I'm going to give you 2 more exercises. First of all, pick your own problem, and then solve it. All you have to do is replace the numbers appropriately here, run it again. You got the code. That's the beauty of code. And that's the beauty of MATLAB code because it's interactive. So it's like a costly calculator. MATLAB is the costliest calculator. Your own problem and solve it. And then check it yourself. You can use 0, 0, 0, 0, but that's a very easy example. 0, 0, 0, 0. Choose something else. You can even change ABC if you don't want to go with this figure. Create your own ABC. And then run it, see whether it works. After that, I'm going to give you another example, which is one step further. When you solve that, you'll be so excited, you'll be calling your parents in the break.
So here we are transforming from mountain frame, translating from mountain frame to car.
Exactly like this, yeah. Just a different example, but the same thing. We're doing exactly what we did here. So all you have to do is, you have to give yourself a problem and know the answer, and then you have to change. You don't have to change A, B, C, because unless you're changing the axis, don't touch that. All you have to do is change the input vector and look at the output and check whether it makes sense. So it does work.
Yes.
Now you're saying, why did they add that extra row?
Yeah.
Because it's needed to do both rotations and translations in the same process. Yeah. I'll give you another problem though before we get to rotations. Take the result and transform it from the car coordinates to the mountain coordinates. So you'll have to figure out what, remember I said, if you're going from this axis to that axis, you have to figure out the F to move that axis back here, right? So now I want you to go in the opposite direction. Here's the result, make that the input vector and transform it back to the mountain coordinates. First of all, what should the answer be? You should get back what you fed as an input, right? So the old vec cm should be the result. I'm asking you to take this and transform it back. So what changes will you do here? I'll let you figure it out. I'll give you a few minutes to change the code and run it. That vector had better land on the original vector. Otherwise there's something wrong with the whole system. So take that vector result and move it back to the mountain coordinates. And remember, t to go from here to here, we have to find f to go from here to here. So it's the opposites rule.
That means we can just multiply with the vector c and p form one transpose thing. Then we can get that.
Well, the answer moves to this spot.
Yeah, like
You can call
the
that
final part will
vec
be
c, and you need to generate vec m. But you'll also have to modify the transformation. If you want, you can insert it here. Like leave that because that's good theory. You can do it here, going back the opposite direction. So what changes should there be here? ABC should be, sign should be reversed. Yeah. So change the sign. So define a new ABC here. Take the result and define that as vec cc, and change this from vec m. You make it vec cc, right? And patch that in here. I'll give you a few minutes because it's a worthwhile exercise. Have you done it? Yeah, just do it. Yeah. Huh? If you just want to modify this code?
Yeah.
When you modify the code, then you know all these comments and all that. If you don't modify it later, you'll say what's going on here. So you can put a note here saying that I'm now transforming it back. You know, then it's cleaner as a document. And then you do rotation, and then do an example, and we'll just about be at the point where we should take a lunch break. This afternoon we're going to do quaternions, so come with a clear head. Don't eat too much because it makes you sleepy. I'm joking. Eat whatever you want. So it's better to write new code instead of just trying to modify it. Just copy, you know, and then change.
So we should get the same point, right, which we got as output first.
Yeah. Got it. Okay. You see why we need TF? Because human beings are very slow, even doing one point. This is not our strength. So let me summarize what you should do to get the right result if you haven't got it. So you create another transform here, maybe you want to call it T-form 2 or whatever, T-form reverse. Define A, B, C, which is the negative of these quantities. And then now your vec CC will be the input and vec M will be the output. And you should get the right result. Okay, so now let's take up rotation. So for that we go back to the PowerPoint, or rather the keynote. Now again, here we are not interested in deriving anything. So we're just going to use a few examples and then figure out the general rule. Okay, here. Oh, this is basically she's reviewing the translation part. So we can skip through this. So how do we transform the k coordinate frame into the j coordinate frame? So what is being done here is the two frames are drawn on top of each other. So if you notice, yk and yj, got it? So there seems to be also xk and xj. C happens to go inside. So can you see that one rotation of 90 degrees is going to align it? So over here it's easier to see because what she has done is she has pulled apart the frames. There is no translation between the two. They just pulled apart so that it's easier to see. Is that okay? So you can see that if I rotate this way, I'll end up in this alignment. Now you've got to be very careful. Is it plus 90 degrees or minus 90 degrees? So for that you have to use, either this rule or the right hand screwdriver rule, because if it's plus 90 and you make it minus 90, everything will go to, will not work. So you have to get the right angle. Okay, so how do I get it? Now we're coming up with some problems whose answers we know first. So consider the origin of the j-axis. So the origin of the j-axis 0, 0, 1, 0, 0, 0, 1. That 1 is, it's a weighting factor. In j coordinates, what is the location in k coordinates? Okay? So origin will be 0, 0, 0, right? It's not going to change. You agree? Because the origins are coincident. But how about ABC1? And you can figure it out. It's easier to figure out when they are pulled apart. So ABC1, A, B, C, right? So the B will correspond to the x-axis here. The A will be the y-axis with the appropriate sign. This one is easy. The Z, there is no change. So here is the answer. Consider the point ABC1 transpose. What is its location in k coordinates? So everybody agree that this is the answer. ABC1 in j coordinate system. Again, I like them to be pulled apart. In this system, ABC1 will be B minus A C1. You agree? And that's true for any B, A, and C. Agreed?
Yeah.
So we want a point in J to be transformed to K. Now it's giving you the answer and then she'll generalize it. So basically FKJ, do you remember the system? What does it take to align the K frame to the J frame? Why is she doing that? Because we want to transform a point from J to K. Here she's considering the opposite. The opposite rule also applies for rotations. So rotation Z minus 90. Why minus 90 and not plus 90? Look at it. Look at the two axes. Right? And also remember, you're rotating K to J. So what does it take to rotate K to J? You're going to come this way, right?
Yeah.
So imagine the right hand rule. It will be minus 90 degrees,
Yeah.
not plus 90. So it's very important. Now computers will do it automatically. For human beings, you have to think and say, oh, what is the convention? So for that situation, this is the matrix. The theta is minus 90, cosine theta. We're not deriving it. I'm just giving you the result. So cosine theta, sine theta, minus sine theta. Okay? So right now we have not done any translations. This is pure rotation. Later, as the final step, we'll combine both translations and rotations. Is that clear?
Yeah.
So this is for the Z case. And then you end up with this. Because cosine of 90 degrees, minus 90 degrees is 0. Minus sine of 90 degrees is 1 here. Right? Sorry. Minus sine minus 90 degrees is plus 1. Minus of minus 1. So 0, 1, minus 1, 0, and the rest of the matrix. It is always the opposite frame rotation. If you want to go from here to here, you need the other F. F is in the opposite direction. Does it work? You can try it out. Use this, give yourself any vector, right? In the original frame, J frame, and see whether it works. 0, 0, 0 is a boring example because it gives you 0, 0, 1. So she runs it, right? Does the matrix multiplication, got it? And it turns out to be correct. It is. This is a more interesting example, ABC, the general case. And the answer, we already know, the answer should be B minus A C1. Try it out through conventional matrix multiplication techniques. And I point out that the rotation angle can be anything. We just assume 90 degrees because it's easy to spot the answer for us as a human being. So where are we? We can compute the F and T matrices when the two frames only differ by translation along some combination of translations along the X, Y, and Z axis. The two frames only differ by rotation about one of the Z axis, right? And the last thing is to combine both of them. But I believe we are doing this particular step, but just the previous step we did in MATLAB also. Let's go and check. Maybe I'm wrong, but it involves no translation and a single rotation, right?
Yeah.
So the same example. So pure rotation only, no displacement. Therefore, I zeroed all these three. ABC is zeroed out. It was a mistake. The example, she used ABC because the ABC will be confused with the ABC, which is the shifting between the three axes. So don't get confused because she used an example with ABC, remember, and transformed it. This is a different ABC. So since there is no displacement, you put 0 here. Theta z is minus 90, got it?
Yeah.
And then I'm calculating the matrix. So here's the matrix, cosine d. Very important. Cosine in degrees, not in radians. So you have to use the meta function cosine d for degrees. Theta z minus sine d theta z. And then you have a 0 and an ABC. Oh, am I putting? Oh, no. I have to put the ABC in. There is no translation, but I want to keep it general, right? So even though there's no translation, I'm putting in the ABC, but its values are 0. So there is no translation, right? Yeah, we don't want to touch that, whatever we have learned from before. Okay, then I take the vector 3, 4, minus 5, 1. The answer is easy for you to figure out. And I transform it. Check whether this is correct. 3, 4, minus 5. So 3, 4, minus 5. 3 will show up in as a negative value in the y column, right? 4, isn't that true? 3, 4. So xk will be 4. Got it? Y will be negative of this quantity. Z will be the same. That goes there and becomes minus. And Z remains the same. Is that right? The result is obvious. 3 becomes minus 3, 4 and 4 are the same, minus 5. So, now we don't know the problem waiting around the corner, which is gimbal law. We're going to get to that this afternoon. And because of that, we have to go to quaternions, right? And nobody uses transformation matrices anymore, except the older game programmers because they don't want to change. So they found a way around gimbal law by other methods. It's painful, but it's a lot of learning for them. So what happens in gaming is you have all these software libraries that you built up, right? And some of them are the personal property of those guys. They don't want to give up on that. Because now if you go to quaternions, now all of a sudden you have to shift your thinking. So that's why they stick to that, right? And so long as it looks good on the screen, people are going to buy their software. They don't care. Okay, let's just get started on the last one. Both. So something, well, I shouldn't say strange, it's not strange, but when you go to rotations, right, you have to define which axis system you're going to use. And in general, there are two systems. One is called the moving axis approach, and the other is the fixed axis approach. We are not going to do the fixed axis approach because it's not very intuitive to use a fixed axis. Let me tell you why. Let's say that this is a plane. Oh, there's no coffee in it because I'm going to turn it around. So this is a plane, right? And it goes like that. It has to take its axis with itself. You can't leave the axis behind.
Yeah.
So when a plane goes like this, the axis has to move with it, right? So the fixed axis would be where it always refers to a fixed axis system, even though it rolls and so on. That's not a nice way of, nobody wants an axis that is not from its own point of view. So even though it's a good academic exercise, there's no point in doing the fixed axis approach. So there is translation also, you see? For the first time, there's not only rotation, there is rotation. See, this is y, but that's x. This is y, but that's z. And there's also translation. So, what does it take? What sequence of moves do you need to compute f? This is the frame alignment from world to gripper. World, gripper. So you have to align gripper to world. Remember the opposite?
Yeah.
So in order to get t from gripper to world, you would obtain f from world to gripper. It's the opposite rule. So obviously, since she's asking for this, the eventual thing we'll do is to take a gripper vector, a point in the gripper world, the gripper axis and put it in the word axis. Is that okay?
Yeah.
So there are many ways of doing the aligning. Any one method where you align the two is okay. You can do different sequences and get the same result, right? So this is just one way of aligning. Start in the world coordinates. So here's the world coordinates. Rotate about xw. See, she's got new color. So the blue is the original, and then the x1, y1, z1 is after you rotate around xw by minus 90. You know the convention?
Yeah.
Right hand rule, right? This is the positive direction of rotation, that's the opposite direction. So we end up with the orange set of coordinates. See here?
Yeah.
We are still not aligned. We are still not aligned. You can check. We've got to go one more step. Then you rotate around Z1. So moving axis is because you're now rotating around the new axis. Fixed axis would be you're always rotating around the original axis. So it's two different conventions which will lead to the same result. But I told you, fixed axis is not the normal axis for planes and so on, because you want to take the axis with you and you want that to be the new reference. So rotate about Z1 by minus 90, call the resulting frame frame 2. So we had initially orange, and then you create a Z2, and we are aligned. We will be aligned after this. So rotate about Z1 by minus 90 again. It's minus 90, call the resulting frame frame 2. So here is 2. And you see that now it's angle aligned. Only then can you talk about translation. You cannot do translation without aligning the axis. It has no meaning. So the answer is not the answer, but the translation part of it is 005. Translate by 005 relative to coordinate frame 2. So remember the second frame that we got is this x2 equal to z2, and now to align it we need a 005. Convenient. She summarizes it for us. First move, second move, third move. There is no, you don't refer to the original axis, you refer to always the new frame axis. So she's just giving us a reminder. That's why you call it moving axis. We don't want to do that, but we have to cycle through slides, fixed axis, fixed axis, fixed axis, fixed axis nodes, summary of the nodes, but we're not interested. The equations are coming up. So this is the, remember we had, for the z-axis we use this, z-axis rotation.
Yes.
So for x-axis rotation, the cosine sign moves to this part here.
Yes, sir.
And for y-axis rotation, it moves here. See? So that is known to us. We're not deriving it, we're accepting the result. So basically, rotation over y, do it this way, rotation over x, do it this way, rotation over z, do it this way. And then, moving axis, forget the fixed axis, the order is different. If you're curious, fixed axis, the order is different. Moving axis, list the moves from left to right. If you say y, I'll say we need to derive the whole thing from a mathematician's point of view. We're just taking the results, right? We're accepting the results. So she says, you've got to stack the moves from left to right. This was the first move, which produced axis number 2, and then we had a second move, which, produced axis 1, x1, and then we went to the second, subscript, and then we put a translation in. So, see here? What do you think this is? The translation, just like before.
Yes, sir.
The first rotation, this one. Second rotation, see? The sine of 90 degrees in different places, cosine of 90 degrees, and then you get the right result. So let's try it in MATLAB, and then let's just run towards the lunch. Yeah, general case of rotation and translations. Yeah. Okay. So I'm using the same example, the one that we just now went through, right? That she hand calculated. We're going to do it in MATLAB. So here it is. You can go back and check. I'm not cheating. So notice in one case, these cosines and sines are coming in a different position. See here? 1, 0, 0, 0, and the cosine starts in the second row, second column. Got it? And for z, it's like the very first example. It is in the top corner, top left corner. So cosine minus sine, sine. Got it? I've just copied from her formulae in the general case, right? I just put it here. And then I put a translation here, which is this. And then I construct the overall transformation matrix. And interesting thing is, even if you do it with a fixed axis result, at this point you will get the same matrix. You have to get the same matrix. So the T form 4 has to be the same. It's kind of interesting because the methods are slightly different. One is moving axis, the other is fixed axis, but that final matrix has to be the same because there can only be one result. You can't have two results based on fixed axis or moving axis. So the final matrix is T form 4, and I multiply it by vec in the gripper, and I get the answer in the word coordinates. And you can check it out, it's right. So this is the traditional homogeneous transformation approach, which was followed for many, many years. Still they follow it. Because the gimbal lock problem only occurs for some extreme cases. If you have a camera, right, and you point the camera up at the roof 90 degrees, you will get a situation known as gimbal lock. You'll see what it is this afternoon. Or you point it at the floor. Most of the time when you have a camera, you're not pointing it at the roof, you might be close. And you might be close this way, you're not going to point it directly vertically. If you don't do that, then you're okay. Nothing bad will happen. You won't get gimbal lock. Otherwise, if you're afraid of that, you should use quaternions. So in this afternoon, we'll see what the problem of gimbal lock is. And then we'll do quaternions. And then after that, we can move on to localization and mapping.